Xinzhou was my former PhD student and currently my postdoc. So he has been studying how to make statistics more rigorous in those high throughput biological data analysis, in particular, how to fix the exaggerated false positives made by some popular differential expression methods, including HR and DESeq2. So today, Xinzhou is going to present our results and our solution. So thanks for the invitation, Alex, and please go ahead, Xinzhou.
Okay, thanks, Jessica, for the introduction. Today, I'd like to introduce a very basic but important task in high-throughput data analysis, the differential expression analysis. I'll first introduce some interesting findings from some real data sets that many popular differential expression methods have exaggerated false positives. And then I will introduce how I like to solve these problems. So here is very, So here is very simple cartoon illustration for the differential gene expression analysis. So in such kind of analysis, we have gene expression matrices from the two conditions, and we want to identify those genes which have different expression values between the two conditions. For example, this gene has higher values in condition 2 compared to condition 1. This kind of analysis is very basic for the analysis of most biological data. So there has already been many differential gene expression methods. Years ago, the core challenge for the D gene identification was the small sample size. And many methods have been developed to solve the small sample size issue by assuming the distributional assumptions. For example, among all the D gene identification tools, DESeq2 and HR are the two most popular ones, and they both assume that the read count values follow a negative binomial distribution. So such distributional assumptions makes it possible to do a p-value from a small sample size. And these methods have been very successful over the last few years, and they have been also used for some large sample size dataset analysis. However, we go back to how they were proposed. We find that these methods were originally proposed to solve the small sample size problem. And the question is, does these methods still work for large sample size RNA-seq data? As we know, recently we have more and more large datasets with large sample size. For example, the large consortium datasets, including GTEx and TCGA datasets, or single-cell RNA-seq datasets. The sample size of these datasets can be hundreds or thousands or even larger. Can we still use those methods proposed for small sample size RNA-seq data for these large sample size RNA-seq data? To answer this question, we use some real dataset to look into, and I'd like to use one immunotherapy dataset as an example to show our findings. The finding is very interesting. We use this dataset where the two conditions are treated and untreated patients, and the two conditions have add up to 100 samples. We first permute the dataset, permute the two condition labels to generate 1,000 negative control datasets. As on these negative control datasets, the condition labels are totally permuted. It means that there are no true DE genes on these datasets, so that we should expect no DE gene is identified by DE gene identification method. However, we find that if we look at panel A, we can see that both DESeq2 and HR identified a large number of DE genes even on the permuted dataset. And the number of DE genes identified is even larger than that from the original dataset. We also find that if we go look at panel B, we see that many DE genes are frequently identified on permuted datasets, or in particular for DESeq2 and HR. If we look at the 50% threshold, we can see that there are hundreds of DE genes which are identified in more than 50% of the permuted dataset. So these results showed that the DE genes identified on original dataset are also questionable. So it is likely that, similar to the permuted dataset, the DE genes identified on the original dataset are also false positives. So if these DE genes identified are false positives, we are likely to make some wrong biological conclusions. Out of curiosity and as a means of verification, we investigate the biological function of those DE genes identified on permuted datasets. So as most biological analysis will do, we do the gene ontology analysis on those genes identified on permuted datasets. And we find that we do have some biological findings from those genes. We find that the top enriched GTEx include the immune-related TENs on those false DE genes. So which means that the researchers will likely be misled by those DE genes, those false DE genes. The researchers, if they look at the results, they may just think that there are indeed difference in immune response between treated and untreated patients, so that they may get wrong biological conclusions. And this result and this consequence is something that we do not deny, and we should avoid such wrong conclusions by control the false positives. This discovery was very surprising to me, and I was very curious why D62 and EGA have so many false positives. Our hypothesis was that the exaggerated false positives may come from the violation of the model assumptions. As we know, both D62 and EGA assume negative binomial distribution. And if the negative binomial distribution assumption is violated, the p-value calculation of these methods may be problematic, so that the FDR cannot be controlled. So what we did was to separate the genes into two groups: the genes which were wrongly identified as DE genes from permuted datasets and all the other genes. For both groups, we use goodness of fit test to fit these genes with negative binomial distribution, and the results show that the genes wrongly identified as DE genes from permuted datasets do have worse fitness of the negative binomial distribution. So this result is consistent for both D62 and EGA. So far from the results, we know that the violation of the distributional assumption may lead to questionable p-values, and the questionable p-values will lead to exaggerated false positives, and those false positives will lead to questionable biological discoveries. And these results show that we should not always use those parametric-based methods for D analysis, especially for D analysis on large sample size datasets. We further look into the reason why these negative binomial distribution was violated for those genes, and we find that outlier is likely a main cause of this violation. Here are two QQ plots for the two genes which are identified as DE genes in most permuted datasets by D62 and EGA. And we find that for both genes, there is a very large outlier within that gene. The existence of outlier make the negative binomial model cannot be well fit and will cause severe problems regarding the p-values. And this will finally lead to the exaggerated false positives. However, there are the Wilcoxon-Rank sum test, which is a non-parametric test which focuses on the median instead of the mean of the measurements. This test is more robust to outliers And if we go back to our previous results, we can see that the Wilcoxon test has no false positives on the permuted datasets. So it seems that we should use Wilcoxon rank sum test, such non-parametric tests, in this large sample size DG identification tasks. And to further verify this idea, we designed some more comprehensive synthetic dataset to benchmark different DG identification methods. In our previous analysis, we only focused on the number of false positives, but this time we also want to evaluate the power of different DG identification tools. We generate synthetic datasets from both GTEx and TCJ datasets. In particular, in GTEx, we do differential analysis between two cell types, and in TCJ datasets, we do differential analysis between different disease status. For all the synthetic datasets, we compared 3 parametric methods and 3 non-parametric methods. And in all synthetic datasets, we find that DSIC2 and EDGA, these 2 parametric-based methods, consistently showed exaggerated false positives. And here is an example of one of those synthetic datasets, which was generated from a hard sample of GTEx dataset. If we focus on panel A, we can see that first, among all the methods, only Wilcoxon can control the false discovery rate under the threshold. And all other methods, no matter non-parametric or parametric, cannot control the false discovery rate. And we can also see that Wilcoxon rank sum tests also have good power. And if we fix the actual FDR, which means that we do not use the claimed FDR of different methods, but we look at the actual FDR of different methods. And when the actual FDR are the same, Wilcoxon actually have the highest power among all the methods. So this result was very surprising to me because Wilcoxon was a very simple, straightforward, non-parametric test. And it does not have any assumptions, and it does not use any fancy models. It's very simple, but it has the best performance. So this result indicates that maybe for large sample size problem, we should go back to some simple methods instead of those very complicated methods, because those non-parametric methods should have good power when the sample size is large. And it has the very good advantage that it does not rely on any distributional assumptions, which are likely violated for biological data analysis. Finally, we want to investigate how sample size would influence the performance of different methods. We fix the target FDR equals to 1% and change the sample size of the synthetic datasets ranging from 2 to 100. You can still see that Wilcoxon is the only method which can control the FDR under target for all the circumstances. If we look at the power, we can see that although Wilcoxon rank sum tests do not have power when sample size is smaller equal than 8, it is as expected because this is the nature of Wilcoxon tests, and it is its main drawback. However, when the sample size increase, Wilcoxon's rank sum test has becoming better and better. And we also find that DSIC2 and EDGA has their best performance in terms of FDR control when the sample size is around 10. And I think that's why we find that these 2 methods may work for some bulk RNA-seq datasets with small sample size. However, for large consortium datasets or single-cell RNA-seq datasets which have large sample size, we should not use these parametric methods anymore, and we should focus on the non-parametric method. So to summarize, for the large sample size DEG analysis, I would suggest to not use DSIC2 and EDGA because of their false positives. And for large sample size data, Wilcoxon-Roux-Exam test is the best choice for its FDR control and power. However, Wilcoxon is not always the best choice. First, it cannot have power when sample size is less than 8. And also, Wilcoxon-Roux-Exam test is a non-regression-based method, which makes it unable to adjust for confounders. To fulfill in these gaps of Wilcoxon-Roux-Exam test, I would like to propose another model-free solution for these exaggerated false positives of DE method. So this another solution is called the Clipper. Clipper is our previous work, which has already been published on Genome Biology last October. This is a p-value-free FDR control framework on high-throughput data analysis. It controls the FDR without assuming any parametric distributions, and it also does not rely on any p-values. I'd like to give very brief introduction to our Clipper method. Clipper takes as input two measurement matrices, one from the experimental condition and one from the background condition. For both matrices, each row is a feature and each column is a replicate or a sample. So in DEG analysis, a gene will be a feature here. Here we define Xj and Yj as the measurements of feature J under the two conditions, and mu Xj and mu Yj as the expected measurements from the two conditions for feature J. Clipper aims to find the interesting features by comparing these two conditions. Here, the interesting means enriched or differential. Here, and enriched features are those features which has higher measurements in experimental condition compared to background condition, and the differential features are those features which have different measurements between the two conditions. Clipper has very simple assumptions. Conditional on the expected measurements from the two conditions, it assumes that the different replicates from the two conditions are mutually independent, and also assumes that different features are also mutually independent. And for uninteresting features, it further assumes that the two conditions have the same distribution. Based on these assumptions, Clipper defines a contrast score, which is one of the two key components of Clipper. Generally, Clipper have two steps. It first constructs a contrast score, which is summary statistic, which summarizes the contrast between two conditions, and then set up a cutoff on those contrast scores. In the following part, I will only introduce a very simple case of enrichment analysis with equal number of replicates from the two conditions. If you are interested in the details of other tasks, you can refer to our paper for details.
So really quick question before you move on. Sorry, could you go back one slide?
Okay.
So one of the second of the assumptions under one is that so are you saying that the idea is not that the individual feature vectors are independent of one another, but rather that the X's are independent of the Y's? That's what you're saying?
Yeah, I'm saying that all these features are independent. Xi is independent of Xj and Y any Y.
So usually our features are genes, right?
Yeah, features are genes.
Yeah. So, but they're often not independent, right?
Yes, and that's why our independence is conditional on the expectation. So it means that if we know that sometimes two genes have high expression together or have low expression together, and these high and low expression these information has been included in the expectation of those genes. So which means that if we conditional on the expected measurements or expected expression values for those genes, the randomness may come from the measurement error.
So what you're saying is that the variation needs to be independent. So they can
variation
they can covary on average, but the variation
expectation is independent. And I think that's reasonable to me.
Okay, cool. Very, I just wanted to clarify. Thanks.
Yeah. Okay. Thank you for your question. I think that's a very important point for this assumption, and I will continue. So I will introduce two contrast scores for the enrichment analysis. The first one is minus contrast score, which is just a difference in means between the two conditions. And the second is called the maximum contrast score, which is defined as the maximum of the two condition means times the sign of the difference in means. So if we look at these two contrast scores, we will find that both contrast scores are positive if the experimental condition has higher values compared to the background condition and negative otherwise. We also expect that the contrast score is higher if the feature is more interesting. And here is a cartoon illustration for the contrast scores. Here we only have two features and two replicates. We can define the maximum contrast score as the maximum of these two measurements, and its sign is positive if experimental condition has higher values and negative if background condition has higher values. And similar, we can define minus contrast scores as difference in means. So we can see that the definition of contrast was very simple. We can use contrast score to summarize the contrast between the two conditions for all the features from C1 to CD, where D is the number of features. And then we can look at the distribution of the contrast scores. According to our assumptions, for those uninteresting features, the two conditions should have the same distribution so that the sign of the contrast score can have equal probability to be positive and negative. So the majority of the contrast scores should be symmetric around 0. And for those interesting features, as in enrichment analysis, the interesting features are those who has higher measurements in the experimental condition compared to the background condition. Those interesting features should have higher values of contrast scores so that they will form this heavy tail. To identify these interesting features, we will set a threshold and identify those features which has higher values compared to their threshold. Identify those features as discoveries. And here is how we define the threshold. The threshold is defined as the minimum of all the possible contrast scores which satisfies this this formula. The ratio of the number of contrast scores which has values smaller or equal than negative t plus 1 over the number of contrast scores greater than positive t. This ratio is smaller than q. So the denominator can be considered as the total number of discoveries, and the numerator can be considered as an estimate of the number of false discoveries. So that the ratio is an estimate of the false discoveries, and we can control the FDR by using this threshold. This is our contrast score and threshold for our enrichment analysis with equal number of replicates, and we have similar procedures for other tasks. In our previous work, we have already shown that by using this procedure, we can have very good performance for DG identification for small sample size datasets. So this figure was in our paper. So this result is on a synthetic dataset generated from bulk human monocyte RNA-seq data, where there are 3 replicates from both conditions. So from the results, we can see that Clipper has very good FDR control and higher power compared to existing methods, including D62 and AJA, but this is only for small sample size datasets. In this way, we can fill in the gaps of Wilcoxon of small sample size problem, and we can also use Clipper as an add-on of existing method to fill in another gap with dataset with covariates. The motivation of this idea is that although the p-values for those methods are questionable due to violation of parametric assumptions, their test statistic may still be meaningful, which means that if a gene has higher test statistic from D62 or AJA, it may still have higher probability to be a DE gene compared to those genes which has smaller statistics. If we can make use of those statistics but not use their p-values, maybe you can still control the false discovery rate. And we can use Clipper to achieve this goal. We can use the statistic from the DE methods as input measurements of Clipper. We can do this. We first do the DE analysis on the original dataset and get the summary statistic for all of the features and treat them as the experimental condition. We can also repeat this procedure on a negative control dataset. Repeat all the DE analysis and get the statistics and use those statistics for each gene from the negative control dataset as our background condition, so that we will have the experimental measurements and background measurements for the two conditions. So here, the negative control datasets can be generated using a simulator or using the permutations. And I would like to show some, and here is another illustration of our idea of using Clipper as an add-on of existing method. So it is just very similar to our previous very simple enrichment analysis with two replicates. So we can get the original, we can do the DE analysis on the original dataset and get the statistic from DE methods. We can also repeat the DE analysis on a negative control dataset and also collect the statistic for all the features. In this way, we can use a simple enrichment analysis to identify those features which has higher values of summary statistics on the original dataset compared to the negative control dataset and treat them as our interesting discoveries. According to the good FDR control results of Clipper, we can use this idea to achieve good FDR control, and we can also make use of the regression-based model of existing DE methods. And here are some of the results. So this is a result on our previous benchmark datasets. So we apply our idea on those GTEx and TCGA datasets and tried to use two different kinds of summary statistics. We use both log-fold change and the statistic to calculate p-values, these two summary statistics from D62 and AGR, and apply our previous idea to adjust the results from these two DE methods and find that when used as an add-on, Clipper can perfectly control the false discovery rate under the target and achieve comparatively good power. We also tried this idea on another dataset where there is an extra covariate, the cell types. This is a single cell dataset with two covariates, cell types, and conditions. We still treat condition. We still focus on the conditions and treat cell types as an extra covariate. This time, we can still see that when applied as an add-on, Clipper still achieves very good FDR control. Although this time power is not so good, but I think it is still reasonable. So from these results, we can see that when use Clipper as an add-on, we can correct the false positive issues of existing methods, no matter whether they have extra covariates. And it means that for this large sample size datasets, a very good solution to solve the exaggerated false positives is to use the Wilcoxon-Ragsam test. And for small sample size and datasets with extra covariates, we can use Clipper as an add-on to fix the problem of existing methods. In the future, I'd like to look into how to improve the power of Clipper and Clipper as an add-on, and to think about the best choice of summary statistics and choose the best way to generate the negative control datasets. Finally, I'd like to thank my advise Jessica and all my lab mates and collaborators, especially Dr. Yumei Li and Dr. Wei Li from UCLA, which helped me with the benchmarking and large sample DE gene problem. And I also thank my former lab mate Yiling, which helped me develop the Clipper framework. And that's all for my presentation. And do you have any questions?